Today starting off with Jianfeng Lu talking to us about sampling strong and log concave distributions using PDMP.
Thanks. So it's a really great pleasure to be here. Actually, this is my first in-person talk at Simons, even though I've been to Simons for a couple of times. And so I decided to talk about something not about diffusion model, but it's related, and also part of the purpose is to introduce. Maybe some of you haven't seen what is the PDMP. Okay, so the piecewise deterministic Markov process, which seems to be a thing that, in some sense, before diffusion model, I guess in machine learning community, the long-driven diffusion is not that familiar with. So maybe at some day that PDMP will also find its way into generative models, which is my one of the hope. And this is a joint work with a grad student at Duke, Yin-Chen Luo. Okay, so let's just focus, kind of specify in the goal. So the goal, the problem is sort of very clear. Okay, so it's so the goal is that we want to generate samples for a log concave distribution, and let's denote it by mu, and it's proportional to e to the minus u. Okay, and where the u is a convex potential, okay, and the u satisfies some lower bound of the Hessian. And some upper bound. Okay, so this is a it's a very clean problem. And now, unlike in diffusion models, we don't assume that we have access to the samples that generated by this distribution. So what you're allowed to do is only the query of the u or greater than u, or maybe in some algorithms, the higher order derivatives of the u. Okay, and in particular, we don't have access to score because otherwise the problem can become completely different. Oh, so I guess for this audience, for people working in diffusion models, it's not surprising that the idea of designing some of these sampling algorithms is to write down a diffusion process and try to discretize it. Okay, so this has been the designing principle for many years in this field. And so one particular example is the so-called overdamped Langevin. Which is a Ito diffusion, so that's where the name diffusion model comes from. So of dxt is driven by the gradient of the potential, or the score, if you like, and then plus some scaled Brownian motion. Okay, and then of course this is a continuous SDE, so that if you want to turn that into algorithm, you need to discretize in time. And if you want exact sampling without any bias, you also need to do some metropolize corrections. And that leads to the so-called Mala algorithm, okay, which is essentially the Euler-Maruyama discretization of this overdamped SDE and plus a metropolis correction step. Okay, so that's where the MA comes from. So it's metropolis adjusted, and this is Langevin algorithm. All right. And now the question that we want to ask today is that what's the complexity of such algorithms to produce a sample that is approximately distributed according to this up to, say, TV error with epsilon. Okay, I hope the setup is clear. All right, so the query complexity for Mala, so the query. So you count the query to this gradient, so gradient u, or in the case of metropolis adjustment, so that you need also query the function value of u. Okay, and the query complexity for this Mala is, after a sequence of work, it's kappa to the square root of d and polylog epsilon. Okay, so as I said, there was a sequence of work, so that I would just give you the citation for the latest two. So the one is by Wu, Scott Schmittler, and Yuan-Si Chen. That's in 22. So what they have shown is that if you have a warm start, then that's the complexity of generating a sample with TV control epsilon. Okay, and then the warm start means that you start with an initial distribution that is in some sense already close. Okay, and then now of course the question remains how to generate such a warm start. And that's being achieved by Xing Ho in the audience and Jason Altshuler back a couple of years before in 24. And also let me just remark that the algorithm they use actually is not Mala. So the analysis of Mala is really this paper. And to produce the warm start, they use actually the kinetic Langevin. Okay, yes?
Is there any results about cold start?
Yeah, this is cold start. Oh, for cold start Mala.
Who started Mala?
Oh, good question. Actually, I don't know. Single, do you know any?
But the mention dependence is worse from a cold start, probably.
Yeah, sure. But I mean, what's the what's the kind of sharp rate?
D rather than root D.
D is kappa times D, maybe.
Yeah.
So it exists, okay. Right.
It's obviously worse than warm start,
Sure,
right?
sure, sure.
So what is the dependency on M and L?
Oh, kappa, yeah, so I forgot to define kappa. So kappa is the ratio, so it's condition number. So it's the ratio between the Lipschitz constant divided by the smallest Hessian eigenvalue. Right. Okay, and also as I guess we heard on Monday, I mean, the rate can be also achieved using the very recent algorithm of force, the first order rejection sampler, which replaces to some extent the metropolis step by the rejection sampler, so that you don't need actually a query of the function value u. It suffices to get the first order query. Okay, so let me also write it down. So with only gradient u query, you can also achieve the same rate. Okay, so same complexity using the algorithm of force. Okay, and then this is by Fan Chen and Xing Ho and Pascalikis and Sasha Wacklin in February or March this year. Okay, and in fact, if you follow arXiv, there was a paper posted last night. Okay, and then improved this rate to combining with some results that maybe I'll briefly mention later. It can be improved. It's a very kind of improvement of the algorithm can improve the complexity to kappa to 2/3 and d to the 1/3 and 1/3 and polylog epsilon. Okay, so this is, I mean, algorithmically, this is a combination of the idea of hypercoexivity. So you're using kinetic. So you're using kinetic Langevin instead, and then plus force. Okay, and if you want to know details, I mean, two of the authors are in the audience. Yes?
So this is the mixing time complexity.
This is the total complexity of creating a sample that has TV guarantee that with error below epsilon.
It's not integration.
No, it counts everything. So that, I mean, like number of time steps that you need, and each step you query something, and so on.
And is the which kind of distance in distribution?
TV, total variation. Okay, questions? All right. And I mean, these bounds are pushing down constantly, and with some help of AI these days, so that, I mean, I think the state of art will change very quickly, so, I mean, so, but this is the state of art right now. Okay, at least till last night. And then, so there was also lower bound, okay, so that which gives us some like target of what to do, what to achieve in the end. So the lower bound also is a work of Xing Ho and his collaborators, and also Jerry Lee, who I think was at least previously in the audience. Okay, so the lower bound is so the query complexity. Actually, this is even achieved by Gaussian, so that this is the O of kappa to the half log d, and so the maximum of this and d. Okay.
Minimum, actually.
Minimum, so yeah. So it's lower bound. So yeah, I should also change the notation. That means O to be omega. All right. So so in particular for the condition number dependence, I mean, so the best, I mean, the lower bound, the best hope is root kappa. Okay. Which is, I mean, if you're familiar with optimization, this may become kind of natural. Okay. So this is because, I mean, this is upper and lower bound for the optimization. For sampling, we haven't reached to the lower bound, but so the hope is that we can get it sometime. All right. So that's the motivation. So now for what I'm going to talk about today, I mean, there are a couple of motivations, okay? So first of all, when I first learned about this result, I think it's kind of nice because it's a high accuracy sampler. I mean, the dependence of the complexity is only polylog, but it doesn't use metropolis, so it only uses the gradient u. This actually reminds me of some other type of samplers that also does that, okay? So only using gradient u without any metropolis, and they actually achieve high accuracy. And these class of samplers are the PDMPs. Okay, so that's, I mean, I studied some of these samplers before, but this kind of give me some motivation to revisit some of these works that we have done before and try to see if we can try to do something better. Okay, and another motivation is that, I mean, again, as you can see from the gap between the upper bound and lower bound, there was still some maybe room to improve for the condition number dependence and also maybe for dimension dependence. So that's also why we want to look at some other ideas in the sampling literature. So maybe beyond, I mean, based on some diffusion or the underdamped version of diffusion. Okay, so by the way, and for those of you who do not know, and so let me just recall the underdamped version of kinetic Langevin here, which appeared a couple of times in our workshop, but I mean, it doesn't hurt to recall. Okay, so you introduce the velocity variable or the momentum, and then it satisfies. This is kind of Hamiltonian dynamics, but then you add in dissipation and fluctuation. Okay, so gamma pt dt and plus root gamma dwt. Okay. All right, and in particular, for example, the kind of cold start algorithm here actually uses the kinetic version of this algorithm, and also this algorithm using the kinetic version. So so it's clear that if you want to achieve better complexity, it's better to use the kinetic version of these diffusions. Okay, so now in some sense, the PDMP actually lives in the same family of these guys, so that you extend it to phase space, and then you try to design a stochastic process on the phase space that mixes, and hopefully faster than the overdamped version, because I mean this is like diffusive scaling. Okay, it's a random walk, so that's kind of why, I mean, you do not directly go somewhere ballistically or deterministically. So you do some random walk, so it takes longer, right? So that's kind of the intuition that why the kinetic kind of schemes or kinetic processes will converge faster. Okay, so that's kind of the similar motivation of these piecewise deterministic Monte Carlo processes, so PDMP. Okay, and there are many of them. I mean, let me just focus on two. Okay, so just give you some idea of how these things look like. And in particular, the first one, I mean, which I will focus mostly, is the so-called bouncy particle sampler. Okay, and it was first proposed by Peters, de Worth, in 2012, and then also made more popular by Boucher, Cote, Vollmer, and then Arnaud Doucet in 2018. Okay. And I mean, let me also write the kind of level of these processes on the level of these kind of things is kind of tricky, okay? Because then you need to describe what the stochastic kind of process is. So instead, let me write a generator, okay, which is of course equivalent, but it's slightly more convenient for PDMPs to describe the generators. Okay, so the generator of these stochastic process, BPS, okay, is given by, I mean, let me write it down and then I'll explain a little bit. I mean, I guess for many of you, maybe this is the first time you see such processes. Okay, so so this is just the drift in the x direction by the velocity. So if you look at this term, this is exactly the same term as this one. Okay, so the velocity just drives the particle moving straight ahead. And then now instead, I mean, in the velocity direction actually does something that is kind of new. Okay, so you have, I mean, this is a scalar, and this means that positive part of this scalar number. Okay, so this is the inner product of velocity and the gradient of the potential, and you only take the positive part of it. Okay, so it means that if your velocity is going like in the descending direction, right, and you don't do anything, okay, so this is, and the number is 0. Okay, but if you go against the potential, so you're kind of climbing up the hill. If you think about that, we are sampling something like double well, you're climbing up the hill, okay, and I mean, actually, even just for a convex potential, okay, you're climbing up the hill. It's not desirable, right? Because you are going to an area that with smaller probability. So you don't want to do that. And then in this BPS, what it does is that once with this rate, it does that, it kind of reflects your trajectory, okay? And by this operator, I mean, I will write down, it bounces the particle, okay? So this is identity, okay? And I mean, I will define B just in a moment, and then the last thing is that there was a refreshment of the velocity. Okay. So now this gamma actually plays the same role of this gamma here in the underdamped Langevin, so this is like a friction parameter. And so I mean, this part of generative just means that I redraw the velocity. Okay, so I redraw the velocity from a Gaussian. So this is what this operator means. And now for this bouncy operator, the B, it is defined as this. So the bouncy operator acting on a observable F. Okay, so in the position X and the velocity V, what it does is that it does nothing about the position. So the particle still stays there, but the velocity changes directions. Okay, so the way that you think about this is that if this is a level set of the gradient, okay, what it does is that, I mean, this is your velocity comes in, and what it does is that it does kind of a specular reflection. Okay, and now in terms of equations, it's you flip the direction of the velocity in the kind of perpendicular direction of the potential. Okay, in the perpendicular direction of the isosurface. Okay, so this is 2. I mean, so that's why you only reflect the velocity component in that direction, right? So this is what this formula means. Is it clear? So now if you want to describe this process as a trajectory on the level of SDEs, I mean, it's not SDE because it's a jump process. Okay, but what it does is that these things are like random events. Okay, and for these random events, the numbers, the coefficient in front give them the rate of how frequently these random events happens. Now, without these events, right, what it does is a very simple trajectory. It just goes straight line for a given velocity, right? Just go straight line. And then you can think of these things as some Poisson process. Okay, so this is a homogeneous Poisson process with a given rate. And when this clock rings, you just resample the velocity. Okay, so this is the description of the third term in the generator. And for a second term is that when this clock rings, of course, this is inhomogeneous. But whenever this clock rings, and what it does is that you just flip the velocity in that particular direction of the gradient U.
So, excuse me?
Yes?
There is no diffusion here. There's no second derivative.
Yeah, exactly. So it's a quite kinetic. But I would say this is kind of like diffusion because you completely redraw the velocity.
Can you explain how pi acts on
pi v is a good question. So pi v of f. Okay, so this is just the integral of f against the Gaussian in v. So in particular, after applying that, actually the resulting function actually does not depend on v. So this is really dummy. Okay. So I mean, this is, even though there was no derivative, but this is integral operator in v. And actually, you can think of this as that if you fix gamma here, and if you only take this part, the OU part of the velocity, and if you send that to infinity, and that actually just redraws the velocity. And so it's the same phenomenon of this guy. And in fact, you can also replace in the underdamped Langevin, this part of the generator corresponds to the fluctuation dissipation by that, and actually then you get the randomized HMC. So it's so there were some connections between this term. Okay. And this is actually a very important comment because I mean, if you only have these things, then there was no ergodicity because you don't any redraw the velocity, and then you can see that so there are some conservative things so that it will not be ergodic. But then because of this redrawing of the velocity, then it is ergodic. Other questions to clarify? I mean, I don't have many materials to present. I mean, just hopefully everyone can understand what I talked about. All right. So, and then, I mean, also just for completeness, let me also mention the Zigzag. Okay, so these are the two most popular PDMPs. Okay, so it's actually a very similar process. And so the only change is that instead of doing things like in the whole vector direction, it only changes the velocity in one of the coordinates. So it's kind of a coordinate descent algorithm. I mean, so it's a kind of a analog of coordinate descent in a sampling world. Okay, and then the generator. So two part of the generator are exactly the same, so that you have the free streaming, and then so the only change is this one. So you do it component-wise, it's coordinate by coordinate. And you replace the expression that we have here with a coordinate version. So you only look at the partial derivative of u in xi, and then times the velocity component there. You only penalize like going against the hill. Okay, and then once that happens, and what you do is you do a bounce. I mean, if you say bounce, but I mean usually in the Zigzag literature we call this flip, but it doesn't really matter. But it's a similar kind of thing as this one, but it only changes the that velocity component, okay, and then you also need to redraw the velocity, and the flip there is you only change the velocity in that particular direction, coordinate. Okay. So in particular for this one, right, if you want, when you want to like calculate rate and so on, so that you only need to query the partial derivative of u. So it's, if you're familiar with optimization literature, there are scenarios that coordinate algorithm is better than the simple naive gradient descent algorithm, and this is also the scenario that this is better. Okay, so I will mostly focus on the BPS discussion because the analysis of the two are kind of similar. Okay, but just a list there for completeness. Oh, okay, I forgot to mention who who wrote it down first. Okay, so this is by Beacons. And Robert in 2019. So actually, the statistics community, after kind of these works, for like 2018 about these PDMPs, there were a collection of works trying to develop new PDMP algorithms and try to apply them to some statistical inference problems, in Bayesian problems. They have some nice advantages. First of all, they are actually high accuracy, so that you don't need to do metropolis corrections. So, they are actually exact kind of process. And you see that you don't need to actually also do integration at all, right? Because the integration of this part is trivial. Just for time, after you elapse some time, you just add that to multiply the velocity with the time duration and add that to the position variable. So, you don't need to discretize anything, okay? And also, they are very friendly to stochastic gradient kind of thing, so that actually, even if you have stochastic gradient, I think also Fan mentioned this for the force, it's kind of similar. For stochastic gradient, they actually also does not have any bias, okay? Even if your gradient is noisy. Okay? But then on the other hand, right, it's not like everyone is using these kind of sampler these days. They still have downside, right? So it's not, they are like a complementary, I would say. One particular downside is that if you wanted to really implement them, then you need to generate these kind of random events, right? Because these are like Poisson processes. And these Poisson processes are inhomogeneous. And of course, if you really want to implement this on a computer, you cannot really just, if you want to like do a finite query model, right? You cannot just query these rates continuously. It's impossible, right? So then you need to know the rates all the time, so then there is no finite query model even. So what you need is that computational realize them. You need an upper bound for these rates, and then use something called Poisson sealing, okay, which I'll discuss maybe a little bit later, and to implement them. And that implementation actually will cause the query. Okay, so it's not completely coming from for free, even though that they use something that entirely different to some extent from these diffusion-based samplers, so that they provide something that one can further explore if you want to reduce the complexity, for example. Yes? Okay, so now as I said, if you want to do complexity analysis, then you need to understand, first of all, if you run this continuous process, how long does it take to, starting from something, cold start, maybe a Gaussian, so to reach a distribution at time t such that it's within the TV distance epsilon to the target. Okay, and then you need to implement these things computationally. All right, so these are the two goals. So now, maybe let me erase this one. So for the first question, okay, so how long does it take? So this is actually some old results that we have with a former student, Lihan Wang, who is now an assistant professor at the National University of Singapore. So let me just write down these results, and I don't think I have time to prove them, but if you're interested, we can discuss later. Okay, so that this is the so-called realization time. So this tells you that how long you really need to run these processes, ideally in continuous time. Okay, so this is trying to work with Lihan Wang. 2020. Okay, and now for the BPS. So one question is that I haven't really discussed that how to choose these parameters, right? So that to obtain the optimal convergence rate, you actually need to choose these parameters also very carefully. Okay, and now for underdamped Langevin, now at least there thanks to the recent development, we understand that you need to choose this rate, okay, of the dissipation, okay, friction, which is the square root of the lowest Hessian eigenvalue. And now for the BPS, turns out that you need to choose the rate which is m times d, okay, and then the theorem says that if you characterize the convergence in terms of chi-square, okay, and convergence to the target measure. So when I was motivating the problem, I only write down the space marginal, right? So that this is distribution in the space degree of freedom for x. But of course, here we extended the phase space so that you have a distribution of both x and the v. And the invariant measure is a product distribution that the x marginal is this and the v marginal is just the Gaussian, okay, which I will denote by rho infinity. And then the up to some universal constant, it is e to the some absolute constant, and the rate is given by m divided by d, and times the initial chi-square. Okay, so this is for BPS, and then similarly for Zigzag, you can also analyze what you have, and then the dissipation rate or the refreshment rate you need to take to be root capital L, and then so it's the same thing, and then the rate changes to m divided by root L t chi-square rho 0 rho infinity. Okay, and both of these results are sharp in general. Okay, so you cannot. It's not a defect of analysis that we get a worse bound. Actually, you can verify that they're sharp. But then I think it's best to understand these things if you compare with what you have in the diffusion cases. Okay, and for overdamped Langevin, you have the, so you have the same kind of bounds, exponential decay in chi-square, and let me just comment that for overdamped Langevin, you have also exponential convergence, and the rate is m. Okay, and remember that m is a small number, right? So root m rate is better than m, could be much better than m. All right, and then for the underdamped Langevin, or the kinetic Langevin, the rate, and this is similar, essentially the randomized HMC is almost a numerical discretization of the underdamped Langevin, idealized the numerical discretization. So they have the same rate, and this is root m. Okay. So now if you compare, you see that in some sense BPS already lose the game because you have a dimension dependence here in terms of the convergence number. But it's not that clear because in the end of the day, you do not really need spatial discretization, temporal discretization for this to implement this process, so that maybe it will win back later. Okay, and also for this process, the rate is also slightly worse. For Zigzag. Okay, but so let me just already I mentioned it already, but let me just remark it again that for Zigzag is really for things that has this coordinate structure. So then you can improve these Lipschitz constant to coordinate Lipschitz constant as the incoordinate descent algorithm, so that it could be much better. Okay, but these are the worst case bounds. All right. So actually, in fact, when we got these continuous time result, and then Li Han did the analysis, we focused on Zigzag because we want better dimension dependence back then. Okay, and we neglected BPS because we saw, okay, there was already dimension dependence here, so that the rate cannot be better. Which, in the end of the day, that is correct, but that's also part of the reason that we need to revisit, because in fact, if you just think about kappa dependence, actually BPS gives you something better. Okay, and let me actually put that down, so that what is the final complexity? Okay, so the BPS complexity, so this is the query complexity from cold start. Okay, so there was no warm start assumption, and this is order of kappa half. If you remember the lower bound, so the kappa matches the lower bound. But because the dimension dependence is here, actually dimension dependence is actually worse than the Mala. Okay, so there's a D. Okay, and then there was something unfortunately that also comes in, so that one has something further. So it's a D log kappa plus log 1 over epsilon. Okay, so there was no trigger. I didn't neglect anything log dependence, so everything is explicit here. So let me also mention that here this thing in the bracket is just because that we are using chi-square here, so that if you do a feasible start, like for example, you locate the global minimum of the potential and then you pick a Gaussian around the minimum, And you start, and because in D dimension, the chi-square divergence between a Gaussian with the final log concave distribution is exponential in D, so that's why we need a D here. Okay, so this is really the convergence realization time that you need from the cold start. Okay, and also, I mean, this is because of that. Okay, so in particular, if you do a warm start, then actually the algorithm complexity is this one. Okay, so the other D factor comes from cold start. And now for zigzag, we also have the estimate, and it's better in dimension, but also as you can see here, it's worse in condition number. Okay, so there was some trade-off. And okay, so and the rest, I mean, the other factor is the same. Okay, it's also from cold start. All right. And now also, I mean, as I said before, right, I mean, our goal is not really, for this work, is not really to close the gap between the upper bound and lower bound, but I think it will give you some promising directions, and because you see that it gives you some improvement if you compare with the upper bound that we have before, right, either in dimension or in kappa, then the obvious open question is how to combine these things together, and maybe you can achieve something better in condition and also better in dimension. Any questions? Yes?
In the bound for BPS,
Yes?
I cannot see the L.
Oh, there was no L. I mean, it's only kappa. So there's a log and log.
No, the bound exponential bound.
Oh, here? No, there was no L dependence. So the rate doesn't depend on L. So it only depends on the lower. I mean, because this is a continuous process, we're not discretizing. So that's kind of, it's natural that the Lipschitz constant shouldn't come in if you think about like all that discretization for the diffusion. Even though, I mean, the origin of these dependencies is a bit different. Okay, so we are not discretizing the trajectory. But I mean, it's kind of natural that in the continuous bound, you don't have the Lipschitz constant. I mean, here the Lipschitz constant comes in is just because this. So that's for a completely different reason.
The other question I had, whether this choice of parameters are optimal or not.
Yeah. Yeah, I mean, they're optimal in the worst case. Let's put it this way. So I mean, as I said, for zigzag, for example, for specific cases, you can do something better. Okay, how much time do you have?
10 minutes.
10 minutes, okay. So now let me actually now comment on one thing, right? So that, I mean, first of all, I mean, you may hope that, I mean, maybe we can remove this factor, right? So that in particular, I mean, the reason that we get this is because the kind of hypercoercivity convergence bound that we have here is in terms of chi-square. Sorry, this is not chi-2, chi-square. Okay, and then, I mean, if we get a similar bound in terms of KL relative entropy, then for sure the initial start doesn't have the exponential D dependence, so that we can get something better. That was also my hope when I started this, looking with together with the student in Chen. But unfortunately, that's not possible, at least for these samplers. And there was an active result by Pierre Momash and Li Han, like maybe a couple of weeks before our work. So Momash and Li Han. So who, I mean, they are basically roughly their results saying that such kind of convergence rate cannot hold in KL. So in other words, you also need to change the process if you want to get entropy decay, and then to remove the cold start dependence. Okay, and by the way, I mean, for these things, they do hold in KL. Okay, so I mean, that's actually the reason that Xinghe and collaborators, and Xinghe Fan and Matthew and collaborators were possible to improve the result. Okay, all right. So now let me just give you some ideas of the algorithm and then maybe a little bit of the proof in time. So as I mentioned that, I mean, the important thing here is that if you want to implement those things, you need to kind of have a good way to do this, I mean, kind of inhomogeneous Poisson process. And now for this business, and now for those of you who work in mass diffusion, right, I try to draw some connection with the theme of the workshop, there is a way to implement the mass diffusion as a continuous time Markov jump process. And then if you do that, then it's actually the similar implementation as what we need here, because you want to drive some inhomogeneous Poisson process. And the standard implementation for that thing, so it has different names. I mean, I like to use the name of Poisson signing, but in that community, in the kinetic Monte Carlo community, it's also called uniformization, but it's roughly the same thing. So this is the implementation that one needs. So it's called Poisson signing. And the basic idea is that if you want to implement a Poisson process, so let's call this rate, right? So it's lambda BPS, which is inhomogeneous, so that it depends on the position and the velocity. And the basic idea of the thinning is that you implement a Poisson process with a constant rate, but it's larger than this. Okay? So you choose something upper bound, okay, which is strictly larger, could be equal, than the inhomogeneous rate that you have. And then in the implementation, what you do is that you implement the Poisson process according to this rate, which is easy because as we learn in elementary probability that if you have a Poisson process with that rate, what you do is just that you draw exponential random variable with the expected waiting time 1 over lambda, right? So you implement, so what you do is that you draw events, you draw candidate events according to this larger rate, okay? So using lambda bar. And then you have, let's say that you have this is time, and this is where this larger kind of rated events wins, okay? So these are the candidate rates that you have. And then you do a thinning. So what you do is that in each of these candidate rate, and you accepted this to be a true event because the rate that we wanted to implement is actually smaller. So you only accept this. So for this candidate event with the rate that is given by the ratio of the two. So it's kind of like Metropolis, okay? But it's, you're not using the potential query, you're just using these rates, okay? So this, by the way, is the reason that for these like high accuracy samplers, you don't need a U. So because the rate is only depending on the gradient U. Okay, so it's first order query is sufficient. All right. So now, as you can see, for this kind of implementation, right? So that you want to choose this envelope of upper bound for the rate. You need to guarantee that this is always larger, right? Otherwise, this is not correct because you're missing some rates. So the clock runs at a slower rate. Okay, but you also don't want to be too large. The reason being that if you generate like a lot of candidate events, to check whether this event is genuine or not, you need to query the gradient U, right? Because you really need, at that point, so I should say that this is S, so that you need to do it at time S, okay? And at that point, you need to query the gradient because you need to calculate what's the exact rate. Okay? So now, in fact, in some sense, if you want to implement them efficiently, in the diffusion-based sampling, the job, or in diffusion models, the job becomes like discretization of the time process, right? And in here, for these BPS, the job really becomes like how to come up with a better rate. Okay, so I would say this is sort of the algorithmic contribution that we did in this paper, so that we just essentially come up with a better rate, the idea of coming up with better upper bounds. Okay, and then what we call this is the so-called window thinning. Okay, so maybe let me continue over there. So the idea is actually very simple. So we need upper bound, okay? And now remember that our rate is nothing but the inner product of V with the gradient U. And now one thing that you notice is that because this is just a reflection, right? So that it doesn't change the magnitude. Okay, so by Cauchy-Schwarz, we can estimate this using the absolute value of the V times the norm of the gradient U. So the only thing kind of important to get the upper bound is just the upper bound of the gradient U. But in our setup of this log concave sampling, we have smoothness assumption so that the gradient U cannot change abruptly, right? So the change can be bounded by Lipschitz constant times the space difference that they have. So this is essentially a total idea. Actually, this was already used in the earlier work by Li Han and myself, but back then we use a kind of worse construction, which is global, so that so the total improvement boils down in some sense to localize the estimate that we use. So this gives us the this algorithm idea of the window thinning. And as I said, the idea is not so hard. So it's just that we partitioned, so this is simulation time. So, by using these estimates, we kind of have estimate of how long the time that we need so that the chi-square is below epsilon square, so that by Cauchy-Schwarz, the TV is below epsilon. Okay, and so that we determine the total simulation time we need. And then we partition that total duration of time into windows with fixed duration, okay, so it's tau. So each of these things window is a tau. And now to come up with upper bound, what we did is just that it's I mean, if you're familiar with some of these optimization algorithms, like variance reduction optimization algorithm, it's kind of similar idea, so that you only query the gradient u. So remember, for the rate, I mean, it depends on gradient u, right? We only query the gradient u at the beginning of each of time interval. Okay, so we call this anchor point, right? So that with the anchor, so we query the gradient ux, let's call this time 0, I mean, just for simplicity, all right? And then now, I mean, we need to kind of estimate of the rate, lambda bar, which could depend on time, during this window. And what we do is that you see that, I mean, kind of we just need really just upper bound of the gradient uxs, right? But of course, I mean, because of smoothness, we have the gradient uxs, I mean, the change, I mean, so this is what we queried already, so we know what that is, okay? And now the change s, okay, so this is bounded by Lipschitz constant times the change in the distance that they travel, the particles, right? But now remember that, I mean, this thing is quite easy, right? So if bouncing happens, I mean, the process just tells us that it's a straight line, right? So that the particle just fly according to a fixed velocity. And even if there was some bounce happening, I mean, the velocity is not, I mean, it changed direction, but the magnitude doesn't change. I mean, when the magnitude changes is when you redraw this velocity, but these things are, I mean, kind of easy to track. Okay, so let's just for simplicity of the fixed idea, so let's assume that there was nothing redrawn during this interval. Then, I mean, this thing can be just bounded by, I mean, so this is, I mean, this can be bounded by 0 to s of the amplitude of velocity integrating time, right? And in particular, to calculate this upper bound, you don't need additional queries. And it's a much tighter upper bound that we used before in our own work, I mean, which actually we do a similar idea, but we not query the windowly, we only anchor at the global minimum. Okay. So, and now, I mean, it comes to be like a trade-off problem, right? So that if the window size is very small, then certainly this upper bound is tight, much tighter. But then you need more queries because your window is small, so that you have much more anchor points. And on the other hand, if your window is very long, then I mean you reduce the number of anchor points, but then the upper bound becomes loose, right? So that you need to like compromise. And then it turns out that if you do that trade-off, the duration of the window is given by 1 over root LD. And then the total time is, you see that it's given by d divided by m, right? So that's total time. So the time is on the order of d divided by root m, and if you combine them, and you get the expected rate. Okay, so I mean, so this divided by that, right? So that you get a d, and then times the condition number of kappa root. Okay, and now I mean, so you may say that, oh, maybe I mean this analysis that we are like doing something silly, right? So that I mean, why you maybe can design a better thinning procedure that does better. Okay, and actually, we also have a proof that you cannot really do that. And so I don't think I have time to discuss that, but you can estimate, so let me just write down somewhere, maybe here. You can actually also try to estimate this quantity. So expected number of the rate, so lambda bps, xt vt dt. So this tells you the expected events that you should have, okay? So it doesn't really matter like how you come up with them, right? So this is just a true expected number, okay? So, I mean, obviously, I mean, your query bound cannot be better than this, okay? And then, I mean, so up to a Cauchy-Schwarz, and actually we can estimate that this is also on the order, I mean, so it's upper bounded by the same thing. So, so in other words, you cannot really improve that much, okay? And I mean, so here, I mean, there's some, yeah, I mean, let me say that this is up to, I mean, so it could not be, I mean, maybe there were some loose things in Cauchy-Schwarz, but I mean, I don't think there was much room to improve for this estimate, okay? So that this is the same bound times the time, okay? Times the co-start, I mean, so, yeah, so the co-start. Okay, so let me just make sure. Yeah, so I mean, so for this proof, there are some interesting stochastic analysis idea that we come up with. If you're interested, we can talk offline, but otherwise, that's the things that I want to discuss. Thank you.
Out of curiosity, this process doesn't seem to be reversible. How do you prove that it's ergodic?
Yeah, I mean, it is not reversible, but I mean, the ergodicity comes from a consequence of this, right? And of course, if you just want qualitative ergodicity, you can also use high-risk argument. But this also gives a quantitative ergodicity. That's actually the hard part of this kind of estimate, which I don't have any time to discuss, but if you're interested, we can talk offline.
Okay, fine.
Just to clarify this last thing you were saying, that's the estimate of the true number of events?
Yeah.
I see.
I mean, expected number of events. So, I mean, in some sense, I mean, so that was answering kind of the question that whether you can do some better thinning procedure so that you can get a better bound. But I don't think there was much room to improve.
Yes? Well, I have a quick question. So the fact that you can take a constant subsize schedule, like in diffusion model sampling, you usually take like geometric towards zero. Is the difference just that you have like global smoothness, while in diffusion model sampling, like you might, the Lipschitz constant might blow up near?
Yeah, I think that's the reason. I think for diffusion model in the usual scaling of the time, that near time zero, the drift field becomes much singular, right? I think they blow up as 1/t.
Okay.
So that's kind of the reason that, for example, if you want to do Euler discretization, you need to shrink the grid. Yes?
So I have a question about the process, bouncing particle process. So how they can remove the accept and reject?
Remove what?
Rejection.
Rejection?
Rejection.
No, it doesn't remove the rejection, right? I mean, you just don't, I mean, you only, if you accept this bouncing events, you do the bounce. If you don't accept it, you just don't do anything, you just move on.
So is this plus operator, the plus,
Yeah.
this one is simulating that or not?
No, this is just a number, right? I mean, the simulation is through the thinning process. And now this number, I mean, so this is actually one nice thing about these samplers. So in some sense, if you think about diffusion, right? Even if you go downhill, I mean, okay, I raised the process. Even if you go downhill, you're still adding noise to it, right? But I mean, for this process, if you go downhill, then they're completely happy. You just go downhill. So that's kind of the reason that why these like kinetic samplers or kinetic processes are faster. Okay, I mean, so it's kind of similar to underdamped Langevin as well. I mean, so you go downhill, then I mean, the noise is only added to the velocity to some extent, so that is added to a high order effect. But I mean, here, like, I mean, there was also something to do with velocity, but the flow itself is just doing something very happy, right? If you go downhill.
Let's thank the speaker one more time.
Thank you.